Hi everyone, today we're going to talk about continuity. The main idea is that a function is continuous if you can draw the graph without picking up your pencil. Formally, the definition of a function being continuous is that a function f of x is continuous at x equals c if 1, c is in the domain of f of x, 2, the limit as x goes to c of f of x is equal to L, meaning there is a limit when x is equal to c, and 3, if f of c is equal to the limit as x goes to c, so the limit has to be equal to the function value. We have to have all three conditions satisfied when x is c for the function to be continuous. Let's look at that in a few graphs. So in this first graph, you can see that we are coming down the graph until we got to 1, and then it jumps up to 2. So this jumping part is this place of discontinuity. If I was drawing, I could draw, but then I would have to pick up my pencil to go to the next dot and write some more. So when we ask where is it discontinuous, you're going to give the x value. So the x value here would be 1. Let's write that in. X is equal to 1. Why is it discontinuous there? Well, the function has a value. We can see that if I put in 1, I do have a y value, but I don't have a limit. The left side and the right side are not going to the same place. So the reason why is the limit when x goes to c, which happens to be 1, of f of x does not exist. All right, our second one. We have a line, but that line has a hole. So that place where the hole occurs is where it's discontinuous, because if I was drawing, I could come across the line, I would have to pick up my pencil to draw this little dot, and then I would draw the line again. No matter how you tried to do it, you would have to come off of the line to add this little point. We'll say there that this is discontinuous, again at x equals 1, but this time for a different reason. I do have a function value. The function value is 2, so f of 1 is 2. I do have a limit. The limit when x went to 1 of f of x was 4. You can see it right here. But the problem is f of 1 is not equal to the limit, so the limit as x goes to 1 of f of x is not equal to f of 1. So there's our discontinuity. This next function, again, I could be drawing the function, so I'll get my laser and we would go along the function, but we have a problem. We have a hole right here, and this hole happens when x is equal to 2. This time, it's not redefined. So when we write in that it's discontinuous at 2, the reason is 2 is not in the domain. Look at this function. This function I could draw without picking up my pencil. I can run all along it and never have to stop drawing. So this says this function is continuous everywhere. In the wording this time, it says where is it continuous, so I didn't ask where is it discontinuous. Again, I'm only giving x values, so when I look at the x values, anywhere from -infinity to infinity, this function is continuous. Same thing happens with this parabola. If I was trying to draw it, I would be able to go all along the parabola, go all the way down and all the way up without ever picking up my pencil. So this says, again, continuous -infinity to infinity. This one I could also draw without picking up my pencil, but it's important to see where did I start. So I started here around x is equal to -4, and then it only moved to the right. So when you give values for the continuity, they have to coincide with the domain. You can't give something that doesn't exist. So I could never say this is continuous -infinity to infinity because I don't have anything on the graph that's less than -4. So let's write that. This is continuous from -4 to infinity. Same thing here with this graph. It has multiple pieces, and I can see the first piece I could come from -infinity, and I'm drawing until I get to -1, right? So when I get around -1, I have to pick up my pencil, and then I have to draw my second piece, right? And that piece goes from x is -1 to x equals 4. Then I have to pick up my pencil again, go to the top of the graph. Now I'm around x equals 4, and I'm going towards infinity. As I'm talking about where I'm going, I keep talking about the domains. And my three pieces were -infinity until I got to -1. Then from -1, I went over to 4. And then my last piece, I went 4 to infinity. So a few quick tips before we jump over to algebra and get away from the graphs. First, lines, quadratics, and polynomials are continuous on negative infinity to infinity, so we won't have any work to do there. Rationals are the ones we're going to have to look at, and generally we're just looking where they're discontinuous, and that's wherever the denominator is equal to 0. So let's look at a few functions. A says f of x is 5 over x. So we have an x in the denominator. We want to say x cannot be 0. Look at a real number line. That 0 broke our graph in half. So I have numbers from negative infinity until 0, and then from 0 to infinity. As you're writing the intervals, you want to make them open and put a union in between. B says g of x is 7x cubed plus 6x minus 11. No issues with that. It's a polynomial, nothing to do. We write negative infinity to infinity. C says f of x is 2x plus 5 over x minus 4 times x plus 6. Again, I'm looking at the denominator, and I say x minus 4 being 0 would give me 4, and I say, well, I can't have that. And then x plus 6 being equal to 0 says x would be negative 6, so I want to get rid of negative 6. You can draw a number line and just put those 2 points on, negative 6 and 4. So you see you have numbers before negative 6. That's negative infinity to negative 6. You have numbers between negative 6 and 4, so that's negative 6 to 4. And then you have numbers after 4, that's 4 to infinity. It's kind of like one more interval than the number of stopping points you have. So I had 2 stopping points, 4 and negative 6, so I have 3 intervals in my answer. D says g of x is 6x minus 3 over x squared plus 4. Now this is one to slow down, pay some time, looking at it. I have x squared plus 4 equals 0. If you try to solve that, you get x squared is negative 4. When you take the square root, you should see, well, I shouldn't be taking the square root of a negative number. We don't do that in this class. So because of that, that's not a bad thing, that's a good thing. That means x squared plus 4 is never going to be 0. In fact, x squared plus 4 is always going to be positive. Think about, you're squaring a number, that makes it greater than or equal to 0. You're adding 4, now it's bigger than 4. So since this won't ever be 0, it means the domain is negative infinity to infinity. 3x plus 7 as f of x is a line, so that is also negative infinity to infinity. And then D says, which is probably really f, I have g of x is 5 over x times x minus 4 squared. Well, first, x can't be 0, then x minus 4 can't be 0. On my number line, here's 0, here's 4. Again, I've broken it twice, so I'm going to have 3 intervals. Negative infinity to 0, 0 to 4, and then 4 to infinity. Once again, all open. Lastly, we need to look at what happens to piecewise defined functions. We're going to start with f of x is 2x if x is less than 3, and x squared plus 5 if x is greater than or equal to 3. So I'm going to point you in the right direction so we start to say, like, what would be important for this function. And what we really need to look at is the place where the function is changing, which is f of 3. So f of 3 is defined in the second line. It's 3 squared plus 5. 9 plus 5 is 14. Now we need to look at the limit. To look at the limit, I need to look at the left and the right side because 3 is where the function changes. 3 from the positive side is again in the second line, so I still have 3 squared plus 5, which is still 14. 3 from the negative side is going to use the first line where x is less than 3. That's numbers smaller than 3, so that we call that the negative side. 2 times 3 is 6. I got 14 on the positive, I got 6 on the negative, which says the limit overall does not exist. Those numbers do not match. Because I don't have a limit, I cannot have continuity. So is f of x continuous at x equals 3? No. So let's try a different function. This one says f of x is x plus 1 over 2 if x is less than 1, and it's the square root of 4x minus 3 if x is greater than or equal to 1. We're going to start with f of 1, so that's our second line, and it says take the square root of 4 times 1 minus 3. Well, 4 minus 3 is 1. I have the square root of 1. I get 1. So I have a function value. 1 from the positive side is that same 1 because it's still 4 times 1 minus 3, and I take the square root. But then 1 from the negative side says use the first line where the numbers were less than 1. So 1 plus 1 over 2. 2 over 2 is 1. Right. The positive side and the negative side both gave me 1. Since they're both the same, the limit is 1. So I have a function value of 1. I have a limit that's equal to 1, which says f of x is continuous when x is equal to 1. My last example says where is the function discontinuous? So I have f of x is 0.5x plus 3 if x is less than negative 4. It's 2x minus 1 if negative 4 is less than or equal to x, which is less than or equal to 3. And it's x squared minus 4 if x is greater than 3. So the points of discontinuity, I have two that I need to check. I need to see what's happening at negative 4, and I need to see what's happening at 3. First off, I can tell they're both defined because there's an equal sign, but what I need to know is the function value equal to the limit? So let's start by looking at the negative 4. F of negative 4, we're going to use the second line to find the function value. I have 2 times negative 4 minus 1. 2 times negative 4 is negative 8, minus 1 is negative 9. Now let's look at the limit as x goes to negative 4 from the positive side. So that would be bigger, and that would put us back at that second line again, 2 times negative 4 minus 1, which is equal to negative 9. When I look at the limit, when x goes to negative 4 from the negative side, I would be using the first line, which is 0.5 times negative 4 plus 3. 0.5 times negative 4 gives me negative 2. Negative 2 plus 3 gives me 1. I'll write the negative 2 there. This is a good place that we could stop. The negative 9 and the 1 are not equal, so this is discontinuous. When x equals negative 4. The second number we need to check is the 3. So just like the last one, I'm going to start by finding f of 3. It's also described in the middle, so I have 2 times 3 minus 1. That's 5. Now let's check out the limit. When x goes to 3, from the positive side. Well, the positive side is the third line, so I have 3 squared minus 4. Those are numbers bigger than 3. 3 squared is 9. 9 minus 4 is 5. If I look at the limit, when x is going to 3, from the negative side, then that's back to the middle line, so I have 2 times 3 minus 1. 6 minus 1 is 5. So 5, 5, 5 is good news. The limit is 5, the value is 5. So 3 is a number that works, it's continuous there, so the only problem I have is that negative 4.